Good day, everyone, and thanks for joining us for NOVONIX's R&D Services webinar on NOVONIX's cell types and cell assembly processes. My name is Lori McLeod, and I am the president of NOVONIX Battery Technology Solutions based in Nova Scotia, Canada, and I'll be your host today. Before we begin, a quick note, today's session is being recorded, and we will send a link to the recording tomorrow. If you have questions during the presentation, please drop them in the Q&A box at the bottom of your screen. We'll have a Q&A session at the end where we'll answer as many as we can. NOVONIX is committed to precision in cell design and assembly, delivering reliable data that drives faster battery innovation. In today's session, Dr. Andrew Van Bommel will walk us through the fundamentals of cell formats, how they're designed, assembled, and tested, and how these decisions influence performance, safety, and long-term reliability. He'll also highlight trade-offs between high power and high energy cells, electrode and tab design considerations, and the impact of electrolyte filling on resistance. By the end of this webinar, you'll gain a clear understanding of the differences between common cell formats and the challenges of stacking and winding, and why precision and quality control are critical to electrochemical performance and lifetime. Our presenter today is Dr. Andrew Van Bommel, Cell R&D Manager here at NOVONIX. Andrew is part of our Research and Development Services team, which supports customers with cell design and prototyping, performance testing, and advanced analysis for a wide range of battery chemistries and formats. Andrew holds a PhD in chemistry from Dalhousie University, where he studied cathode materials under Dr. Jeff Don. He has also held roles with 3M Canada and Salient Energy, and now leads a team of battery scientists at NOVONIX focused on prototype cell design, testing, and analysis. With that, I'll turn it over to Andrew to take us through today's topic.
Great, thanks, Lori. Yes, as Lori said, we're going to be talking about different cell types, at least the cell types that we use in our prototype cell line at NOVONIX, and go through the cell assembly processes for those different cell types. And that's under the NOVONIX R&D Services umbrella. Just an outline of today's presentation. So I'll go over briefly what NOVONIX is and how NOVONIX R&D Services falls under the greater NOVONIX company. I'll go through cell types, mainly talking about stacked and cylindrical cells today. A quick slide on coin cells, and then just a quick discussion on wound pouch, just an image there. And then the cell assembly processes. So for coin cells, just assembly and some testing data. Then stack cells, so that would be both for stack cells and cylindrical cells would be the design, the electrode preparation that's required. In terms of stack cells, the stacking, welding, pouch sealing, quality control, and some test data. And then cylindrical cells, that would be electrode preparation, which would include slitting, winding, welding, crimping, and quality control for that as well. And then I'll just summarize the two stacked and cylindrical cell designs and how we go about those assembly processes. So an overview of NOVONIX Group. So there's three separate divisions. The NOVONIX Anode Materials Division, that's leading domestic supplier of synthetic graphite. And this is a large-scale and sustainable production operation. This is located in Tennessee. And then we have the NOVONIX Cathode Materials and the NOVONIX Battery Technology Solutions divisions. These are both located in Canada. So the Cathode Materials division is commercializing a patented synthesis technology, and this is making NMC with all dry, zero waste technology. So as opposed to the traditional co-precipitation process that has high amounts of water waste and other waste streams. So there's a pilot line there to produce that cathode material. We're looking at the RHK furnace in this image, and that pilot line is capable of producing 10 tons per annum capacity output. Within the Battery Technology Solutions division that we are located in, we have two groups. So one is developing the industry-leading high-precision coulometry cell testing equipment. We call it UHPC. So you can use this equipment, these cyclers, to determine how long your cell will last in a very short period of time. So this is world-leading cell testing equipment. And then we also, with the group that we're in right now, is the R&D services. So we have an in-house pilot line. So during the last webinar, I discussed coding and mixing and coding procedures. So the next step is to make the cells from those coatings. So our pilot line makes the coatings and the cells, and then our scientists do the cell testing and have all the expertise to accelerate your development programs. So within the R&D services group, we have a team of experienced battery scientists. So these are many scientists with their masters and PhDs in battery science. So a lot of background and expertise. We have engineering teams with both R&D and mass production experience. As I mentioned, we have the fully equipped prototyping facility, and we'll go through that, how the cells are made today within that facility. We have thousands of cell cycling channels, so we have a large capability of testing any cells that we make with your materials. Previous engagements, they include various a lot of lithium-ion battery chemistries, and also most recently a lot of different sodium-ion battery chemistries. We work at formulating electrolytes and additives and testing the effect of having those different additives in different formulations. We test conductivity enhancers, so maybe different additives to improve the conductivity of the electrodes, also different separators, different current collectors, and more. So many different projects. So the benefit of working with us is it saves the large capital expense in standing up your own prototyping facility. We have our own dedicated production staff, so we have a fantastic staff on site who do the coding, mixing the coding, and the cell builds. They do an excellent job. We leverage knowledge from industry professionals. We're able to, as I said, accelerate R&D programs. An important group is our project management function. So they ensure every customer that everything is, all the timelines are met and the deliverables are met as well. And we have a highly interactive engagement. We welcome you here for your projects, and our scopes are very flexible. So they may include electrode only or cell only, or all the way to making cells with your materials and doing testing. So now I'll go over the different cell formats that we make at NOVONIX. So first is the coin cell, and this is similar to a button cell found in your car remote. This is in the 2032 format, and we generally make half cells. So this would be using lithium metal or sodium metal more recently as the counter electrode. And at times we do make full cells in this format. It's a little less reliable than our other formats for full cells in a coin cell format. For stacked pouch cells, these are both single and multi-layer pouch. So we'll discuss this today, how these pouch cells are made. The size of the jelly roll is 42 by 60 millimeters in this case for the smaller format of our stacked pouch. And for the multi-layer pouch, generally we're between 1 and 5 amp hour for the capacity. We also have cell stackers and the equipment to make those electrodes for a larger size. So this would give a stacked pouch between 3 amp hour and 20 amp hour capacity. And I mentioned also like single layer pouch cells we also make. So I have a quick discussion on that. That might be as low as 80 milliamp hour for a single pouch cell. So that's just a single layer there. We won't be discussing wound pouches in detail, but we do make wound pouches both in the 20 by 30 millimeter format. So that's the dimensions of the jelly roll here. And then we also make it the 40 by 60 millimeter. So in the 20 by 30, that might give you 200 to 400 milliamp hours, and the 40 by 60, 1 to 3 amp hours. So anything we discuss about it, the wound pouch is sort of a mix of the cylindrical and the stacked, in that it's comprised of 2 electrodes that are wound around, but sort of a squished jelly roll that you see in a cylindrical cell. and then they're inserted into a pouch like the stacked pouch cells are before filling. You can see the tabs have the adhesive area there, so there's proper sealing at the pouch. And then we also make cylindrical cells in both the 18650 and the 2170 formats. So first, just looking at our coin cell. So one slide on this, an exploded view of the coin cell. We have the can bottom. The electrode is punched, weighed. You can see some curl to there because it's only a single-sided electrode. In this case, this is a cathode, I believe. So that electrode is placed on the can bottom. And separators, we use two separators. We use tweezers to handle this in the glove box. So there could be, we don't want any shorts. We do more handling of the separator, obviously with the coin cell than we do with the other cells. So we have two separators to prevent those shorts. We have a counter electrode, so this would be lithium. Here's a picture of lithium. This was taken through the glove box window. It could also be sodium. We have the spacer, so the electrolyte is put on the separator. The lithium is pressed into the spacer usually, and then that assembly is placed on top of the separator with the lithium or sodium in contact with the separator. A wave spring to ensure good pressure on that stack, and the can top. You can see there's a gasket around that can top, so that part of the gasket goes face down on the assembly. We have to make sure that there's no contact between, say, the spacer and the can bottom, so there's no short, especially with anode coin cells. And that assembly is crimped, so that means the can bottom, that edge of the can bottom is crimped around that gasket, and that performs a good seal, or that makes a good seal so that we can do the testing. So here's some examples of some cells that were tested using coin cells. So this is NMC 811 in a lithium coin cell, charging between 2.8 and 4.3 volts, and discharging back to 2.8 volts. The C rate is C/20 in both charge and discharge direction. We generally don't put CV steps on that first charge and discharge, and this one was done at 25 degrees. And this is generally what we see for any NMC 811, which is usually around 83% nickel in that transition metal layer. Here's another coin cell, some more data on hard carbon in a sodium coin cell. In this case, it's sodiated, the hard carbon is sodiated from OCV, which looks maybe around 1.5 down to 5 millivolts. And then there's a CV step until C/50, and then desodiation at C/20 again, up to 1.5 volts. So we typically use coin cells to determine first cycle metrics for a full cell build design, but often we want to get extended cycling from coin cells. But in that case, low mass loadings are required. So here I have a graph of an NMC 811 lithium coin cell cycling at C/5, 25 degrees, and with a normal mass loading. So this would be a good mass load, industrially applicable mass loading of 18.5 milligrams per centimeter squared. We get rapid fade with cycle number. And the reason for this is because that the lithium impedance builds up with cycling. So we get capacity loss that's just due to the lithium impedance or lithium resistance building up. If we don't want that to happen, we just have to slow down the rate. And you can do that just by slowing down the rate or the current, or if you want to just slow down the current or decrease the current, you could also just decrease the mass loading. So we can get, if we use a reasonable rate of C/5 for this cycling, we need 3.8 milligrams per centimeter squared, and we get reasonable cycling. So this is 500 cycles at C/5. We're still above 80% capacity retention. But if we do want to see either, eventually this will roll over because of that impedance from the lithium side. So full cell data is required for even further cycling. And just to let you know, this rollover is even worse, seems to be for us even worse in the sodium case. So we have to be careful about what current densities we see, or we'll get that rapid fade. So moving on to a full cell, the simplest pouch full cell would be the single layer cell. So I have a side profile here. We have the copper current collector, and on that is coated a graphite electrode. We have aluminum current collector, and on that is coated the NMC electrode. And in between, there's a polyethylene separator. So each of these single layer pouches has a single unit each of the anode that you see here and the cathode that you see here. When we make these single layered pouches, these use calendar coating. So that's when they're pressed under pressure to ensure that there's good compaction density of the electrode. But the issue with this is that there's a lot of curling when you do perform that calendering step. So there needs to be extra work in this assembly process. So we have a few jigs and a few ways to assemble the single layer pouch. And here's the final single layer pouch. And in this case, the tabs are welded in the same way onto these uncoated areas in the same way as a multi-layer pouch, but there's only one current collector. So similar weld settings can be used for the single layer pouch as for an 18650 build, for example, for the ultrasonic weld settings. So this stack is placed in the pouch as shown here, and then it's sealed along these edges as the same way as multi-layer pouches, and then it can be filled. So here's some example testing results. When we first started testing some of our single layer pouches, here's some formation data. I just did a zoom in here of some of the formation data initially, and we found that with normal stack pressure, we had a strange bump on formation on that charge profile. And we figured out that that bump was due to possible formation gases being trapped in pore wetting on the electrodes. And so we were able to get rid of this by pushing out the formation gas in a way by increasing the pressure even higher than our stack pressure for multi-layer pouches. So this formation graph here was done at 60 psi stack pressure. So our standard formation is a hold at 1.5 volts. This is the wetting step for 24 hours. And then all these are C/20, so a charge to the upper cutoff voltage for 811, this would be 4.2 volts. Discharge and then charge back to 4.2 volts. And then there's an open circuit step that we use to see that relaxation current. It can show the quality of the cell and if there's any soft shorts in it as well. And then a discharge to a safe voltage prior to degas. So these single layer pouches there's two formation curves over here. So there's excellent formation for those when it did have the higher stack pressure. And then we did UHPC cycling on that. So using NOVONIX UHPC. And there are some differences between one and the other cell, but we do see this sometimes as well with multi-layer pouches. There might be more differences with single layer pouches because we only have that single layer and there's less evening out of slight differences in mass loading. But we're getting above 99.9% Coulombic efficiency, which is higher than some commercial cells. So here's an excellent single layer pouch. If we look at long-term cycling data, so these cells afterwards were put on long-term. That's why you don't see the normal larger decay at the start of long-term and then the flattening out. So you just see a flat discharge capacity versus cycle number. So this was C/3 cycling at 40 degrees, and we're above, approaching 98% capacity retention at 250 cycles at C/3. So this performance is similar to multi-layer pouch cells. The reason why one would use single layer pouches instead of a multi-layer pouch, one of the big reasons why is if our customer cannot provide enough active material for a full mix and coating run. So in that case, if they cannot provide enough cathode material, for example, we can hand coat that cathode material, match it with a machine coated anode single-sided, and then make single layer pouches. So again, just to summarize, these single layer pouches have less precision than multi-layer pouches, and they're a bit more time consuming to build, but if needed, we can make them. So looking at the multi-layered stack cell design, so if we looked last at the single layer pouch had single-sided coatings, so the multi-layered stack cell would have double-sided coatings. So starting from below again, here's the copper coated on both sides with graphite, polyethylene separator, and the aluminum coated on both sides with NMC. Here's a typical multi-layer pouch cell in the side profile. So we would have 7 anodes and 6 cathodes. So here are the bookended anodes on each end, and they're separated by that polyethylene separator. And this would be about a 1 amp hour pouch cell with the smaller, around 42 by 60 millimeter sized stack. So in reality, these separators are not in the stack pouch cell are not just single sheets. They are Z-folded sheets. So here's a very rough side profile schematic of the Z-fold construction. So you can see the Z right there. There's a anode and a cathode, and the separator will be separating those anodes and cathodes. Clearly, this is expanded, so a real pouch cell would look like this with the 7 layers of anode and 6 layers of cathode. To prepare these electrodes, continuous coating is used. So for the slot die coating, we can coat intermittent or patch coating, but we can also make we could also do a simpler continuous coating. So this is used for stacked pouch cells, and you can see this continuous coating, there's margins, areas where there's no coating. So that's where the areas where the tab gets welded to are. So they're just indicated by those yellow punches there. So here's just a schematic of anode punch. So you'd have the copper to be able to weld on. When we finish coating and calendering, typically we sheet this material, so in 200 by 200 millimeter sheets, and then we have a die set that's used to punch, in this case, 8 electrodes from one of those sheets. So here are 2 of those electrodes shown. So these are double-sided electrodes. So in our prototype facility, there's a lot of manual intervention. So this moves along, and the die punches the sheet, and then the operator takes each individual electrode out and then loads it in the carousel for stacking. So now I'll show the electrode stacker that we use. So the center area is the stacking area with the separator. So it has 1 roll of separator used. On the left, here's the carousel with the cathode electrodes. And on the right, here's the carousel for the anode electrodes. So the GIF on the upper right shows that stacking process. So suction cups, which are shown as I'm indicating right here, are used to grab that anode. So it's from the carousel out of the frame here, and it brings it to this area. And then that anode is grabbed and placed on the stack. And then the separator moves, and then it does the same to the cathode. And as that happens, the separator moves over the anode and then over the cathode, and that continues. So the stacker can be programmed depending on what capacity is required, and that will also change what the stack height is as well, which we'll discuss later as well. So that continues until the program is done and the capacity desired is reached. So here's the final cell shown once again. In stacked pouch cells, the tabs are welded by ultrasonic welding. So this has, here's the weld horn, the weld head, some cooling air there, and the bottom is the anvil. So the weld head drops down and ultrasonic vibration is applied, and that makes the weld of that tab material onto the current collector. In the case of a multi-layer pouch cell, there might be 7 or 6 current collectors to be welded. So the weld energy and the weld power needs to be selected such that that gives a good weld. So the weld power is a function of the force applied, which is that compressive force normal to the amount of vibration, the amplitude, which is the displacement of that vibration, and the frequency of vibration. So again, in those stacked pouch cells, many layers of copper or aluminum are welded simultaneously, and it's also welded to the tab. So nickel in the case of the copper or the anode tab, and aluminum in the case of the cathode tab. And you can see here that so these are the weld settings that were selected for a different number of layers. So they were selected by design of experiments, and then selecting a weld energy, and then doing a tear down to ensure that the weld was good. And you notice that when we get to higher number of layers, clearly more weld energy is required. So the next step of stacked pouch cells is pouch forming and sealing. So first, a pocket or a form needs to be formed on the pouch material. So this pouch material is aluminum foil encased in polymer. And so when that pouch is formed or that pocket is made, we can achieve a max depth of about 5 millimeters. If we go higher than this, there will be wrinkles and possible areas where electrolyte can leak out of. So to increase this depth where we can place the stack, we can use this clamshell design. So in this case, if the stack is placed inside the pocket, it can extend a little bit so then the other side also has a pocket to encase that stack. So the pocket has to be made so that there's good alignment of the tab and the insulator. So there's a piece that melts, an insulating piece that melts on the tab, and also the pouch material is melted too during the sealing process. And this ensures that there's good sealing all around the pouch material. So here's a finished pouch. So the stack was placed inside the pocket. The tabs are located there, and the seal is complete. And this, in particular, this one is a dry cell, so there's no electrolyte there. So we tend to do a quality step where we seal all the sides under vacuum. And then the next day we check the cell to see if there's any leaks. It would no longer have this close seal and this nice vacuum seal. So if it seals like this the next day, we know it's a good cell, and we can cut it open and start filling with electrolyte and do the next steps. So some issues, quality control issues for stacked pouch cells. Here's an issue of separator tearing during the Z fold from those metallic fingers that grab the separator. Wrinkles in the tape and the separator. In this case, there's poor anode alignment, so we want to be sure that the anode has an overhang. In our case, we do 1 millimeter overhang for both of our cylindrical cells and our stack cells. In this case, the stack is not tight, the tape is too loose, so the tape will have to be adjusted when the tape is applied. And here's what I was mentioning. If the pouch formed is too deep, there could be damage on the corners. That could be an area where there's electrolyte leaking from. Here's some cases where there's holes, and another case where there's wrinkles in the seal. So these cells would have to be rejected, and more care would have to take place to get good quality pouch cells without these defects. In terms of testing the pouch cells, we weigh our pouch cells. So after filling, we weigh those pouch cells underwater before and after formation, and that allows us to determine the volume of gas generated during formation with Archimedes' principle. We can also do this after testing as well to see the amount of gas formed after testing. For our fixturing, we fixture the cells. So we have two plates here, an upper and a lower plate. And there's springs with a known spring constant applying pressure to the stack. And by varying the height of the spring, we could vary the pressure applied to the stack. So typically when we're testing NMC graphite cells, we run around 10 psi. If we're doing silicon cells, we might go 30 or 60 psi, depending on the amount of silicon in the anode. So here's some example testing results from some of our stacked pouch cells. Here's some NMC and silicon carbon. Silicon carbon and graphite is in the anode for these cells. These are 12 formation curves, the same formation that I showed before. Yeah. So these are 12 curves overlapped. And you can see that this is excellent control, excellent consistency within those cell groups. If we zoom into this section here, we see the very little differences in test time, which would correspond to very little differences in capacity. And so this consistency is from mentioning that last time in last webinar, being very careful of controlling mass loading in the anode and the cathode. So this is careful control of that mass loading and quality checks during the slot die coating process. And then also having high quality and precise punching, welding, stacking, filling, and stack pressure. And the term for cylindrical cell design, the cylindrical cell electrodes, when wound, is known as a jelly roll. And here's an image of a jelly roll on the left. And so we can clearly see how that name was derived from. So there's a stack of the separator, the anode, a separator, and the cathode, and that entire stack of 4 pieces is continuously wound. And again, this is double-sided anode and double-sided cathode. So I'm showing outsourced CT scan of one of our 18650 cells. You can see if you zoom into this section here that you can see the stack. So we see the very dark areas are the NMC. So where I'm indicating here, the NMC, the aluminum NMC, and then the lighter areas is the graphite, copper, and graphite. So you can see that this stack, if we do a cutaway of this, corresponds same to the stack that I showed of all the different layers for the multi-layer pouch cell. So we have all those layers in contact. In this case, it's all from one single piece, like a long piece. I'll show that next, of anode electrode and a long piece of cathode electrode, as opposed to the stack cell that were 7 anodes and 6 cathodes. So to prepare the electrodes for cylindrical cells, we don't use a continuous coating, we use a patch coating. So in a patch coating, there's an area or intermittent coating or skip coating. There's an area that has no electrode coating, shown here. And then after that coating is finished, the electrodes can be slit. So they're slit to size that will, that height will fit as the jelly roll into the can. So the reason why there's patch coating is that area will be required for the tab welding. So here's an image of our electrode slitter. And electrodes are slit down web, so those areas can be welded. Here's a cathode, and you can see the slitting blades here, and then those slit pieces can be wound up, and then later on they're trimmed to fit into the winder for the jelly roll. So here are some images of prepared electrodes. Here's the anode. The anode's a bit longer, so just for scale, that's about 600 millimeters. So all that 600 millimeters will be wound into the jelly roll shown here. So there's the anode prepared and the cathode prepared. So the anode and cathode tabs are ultrasonically welded. Here I'm showing the anode tab, the nickel tab. And then tabs are taped over the weld areas, and those edges of the electrode coatings are also taped. So this tape step is necessary to prevent both those weld spots. So you see 1, 2, 3 weld spots in the anode electrode. So this tape prevents them from poking holes in the separator. And so that's fire safety protection for the cell. So this is just going over jelly roll winding for those cylindrical cells. So again, as I said, there's a stack of 4 layers. So there's the separator, there's the bottom separator there. And these both separators are around a mandrel. So the anode can be placed here, the cathode placed on the top, and those 4 layers are wound together. So this mandrel spins and those 4 layers are wound, forming a finished jelly roll. This is just showing the cathode placed on the top with an electrode alignment guide shown there, so everything is aligned. Again, the same thing, the anode has an overhang of 1 millimeter on each side. And then the separator further has another millimeter overhang on each side. For welding the anode tab, this is just some pliers holding a nickel tab. This is not how it's welded. It's just showing the nickel tab placed on the bottom of the nickel-plated can. So in reality, the nickel tab is in the bottom of the jelly roll. And to be welded, the jelly roll is inserted. So that nickel tab will be on the bottom of the jelly roll. And a mandrel is placed, and then that tab will be resistance welded. This welder has acceptance and rejection criteria based upon the weld energy imparted to that weld. So this will let the operator know if it was a good weld or not. And they can also look at the bottom of the can, and seeing that dimple is more evidence that there's a good weld on that anode. For the cathode tab, the laser welding is used for those aluminum tabs to the aluminum header cap. Here are 4 cells, and this is put into the laser welder, so those welds can be done. So laser welding can cause some weld splatter, so it's important to cover the cell to prevent that splatter from going inside the jelly roll, which could cause shorts. We can do some quality checks of that weld onto the header. So one of them is just to pull on that weld. So we want that weld to break, or we want that metal to break at the bulk metal and not at the weld. So this shows that there's a good quality weld there. So after the welds are finished, this is an 18650 ready to crimp. We see the header there with the gasket, and so we need to crimp the top of the can over that gasket, just like we saw earlier with the coin cells, and that will finish the crimp. Of course, this is after filling the cell. So here's a manual crimping tool that seals the top of the can over the header. So there's a die in here that causes that good seal. And we can see this good crimp seal. So the gasket there is inside here, and that crimp is over that header there. So we have a good seal. So here are some issues that can arise during production of the cylindrical cells. In this case, we mentioned that that separator has to have a 1 millimeter overhang from the anode. In this case, those electrodes are protruding outside the jelly roll. So we have to check the winder to see if everything's proper here to fix this. In this case, the separator is damaged, and this reveals the electrode. So we have to ensure that there's enough wraps and there's no damage of the separator revealing the electrode. We have to ensure that during that laser welding process, there's no welding or distortion of that weld or asymmetric welds with a small contact area. It has to be good contact, and we can check that by that hole test. And here are some examples of pore crimps. In this case, there could be too much height of that can. So either that can begin to wrinkle or the can buckles. So we see that on the side of the can here. If there's not enough pressure, we can see that the plastic is not fully folded into that crimp. And clearly this one is a fail because that cell did not go through that center ring into the die. So you can see that gasket poking out there. So here's a good quality cell. So this outsourced X-ray CT image shows the cell. It has a good alignment of the electrodes. Here's the cathode Z fold. In our manual assembled prototype cylindrical cells, we have one more fold than would be in mass production commercial cells. And just to let you know, for safety, the cylindrical cell header is designed to electrically disconnect if the internal pressure exceeds 200 psi. And then even if there's more buildup in pressure, the vent will open if it exceeds 450 psi. So there's some safety design to these cells as well. Here's some examples of some electrolyte filling and how electrolyte filling is done in cylindrical cells. So these are NMC A11 and graphite 18650 cells. The electrolyte is shown here. And initially, the approximate electrolyte film volume is determined by calculating the pore volume of all the materials. So this would be the separator, the anode, the cathode, and the mandrel volume, or the core volume. And then we can adjust that by going more and less than that fill volume. And then a good check to see if the fill volume is good is to start at a much lower fill volume and continue to make cells with higher fill volumes. We do a ACR measurement, which is done with a Hioki instrument at 1 kilohertz. After formation, it's 50% SOC. So if we do that post-formation ACR, we can see that resistance will decrease as the pores are completely filled, and then it will stabilize, it will flatten out. So in this case, in this test, we noticed that if we fill this cell a little below 3 mils, we have a higher ACR value. But if we continue to increase the fill volume, this decreases that ACR value. So we want to ensure that pore volume is filled, but clearly not to overfill the can. So just to summarize for today, so this is the cell assembly process post-coating. If you want to see more details about the mixing and the coating process, that would be in our previous webinar. So in terms of stacked pouch cells, we initially compress the electrode. We punch the electrode, and we have that 8-electrode punch for the smaller format stack cells that we make. That stack is done with a Z fold with the one separator roll on the stacker, which Z folds between the anodes and the cathodes. Both the anode and the cathode tabs are welded ultrasonically. So the anode would be the nickel tab and the cathode the aluminum tab. And those tabs have that little piece of polymer material that will melt along while the pouch is sealing. That allows it to provide a good seal. The laminate is heat sealed on 3 sides. Since it's folded over, the 3 sides would finish the heat seal. The last side is heated and sealed with vacuum. And we do a check, that overnight check, to ensure that there's good sealing of that pouch cell. Afterwards, it's cut open. It's also vacuum baked. So that would be after only 2 sides were done. So it would be vacuum baked to remove all the moisture. Then the electrolyte would be filled into the pouch cell. This is a vacuum electrolyte fill. Then formation, degas, and then testing. In cylindrical cells, the electrodes are compressed in the same way. The electrodes are slit, so they're slit down web, and that width is the height of the jelly roll of the electrodes in the jelly roll. Then the anode and the cathode tabs are welded. So the electrodes again are patch coated so that the uncoated area will have the area so the anode and cathode tabs could be welded on. The tabs are taped to prevent any shorts. The jelly roll is wound. So this would be those 4 layers. So separator, anode, separator, cathode. That jelly roll is placed in the can. The mandrel is put down into the jelly roll, and the anode tab is welded to the bottom of the can with a resistance weld. And for the cathode tab, it has to be welded to that to the top of the can or to the header with a laser weld. And after that, they're also vacuum baked, and there's enough electrolyte fill. The cells are crimped and formation is done. In this case, there's no degas for our typical projects. So just to go over again what we can offer. So our experience, we have a world-class team of battery experts to support our customers. As I mentioned, we have a wide array of expertise in engineering, metrology, and electrochemistry. We have extensive knowledge in lithium ion, sodium ion, energy storage in general, and engineering fields. And we have experienced researchers from across the industry. In terms of project support, we engage with our customers in a variety of ways. So we can help out with project scoping, and we could work back and forth with whatever project you have in mind. We work on cell designing very often and help design your cells to evaluate your materials. We can test and evaluate different protocols that will work with your materials and your cells. And then after all this is done and the cell builds are done and the cells are being tested, we provide analysis of the process and of the performance data, the outputs that we get from the cell testing. We can make recommendations on your materials and then also make recommendations for process development. So that's it from me today. Thank you.
Thank you so much, Andrew. Now we'll move over to the Q&A period. First question, what is your recommendation for the spacer's material type used in the coin cell? And would you expect any corrosion that may occur when stainless steel 304 or 316 is used?
Yeah, so we use stainless steel, and I'm pretty sure it's 304. And in typical cells, we don't see any evidence of corrosion. So this is using LiPF6 or sodium PF6 salts. There could be a case where if FSI or TFSI is used, there might be some evidence of corrosion. And even though FSI and TFSI are known to corrode aluminum, something like FSI might corrode. I think there's been some indication that it could corrode steel even more than aluminum. So we have worked before with FSI with aluminum-clad hardware. But yeah, that would just be evaluated on a case-by-case for each project. But in general, for PF6 alone, we don't see any evidence of corrosion. And as you saw with that cathode coin cell that can last with CR5 many hundreds of cycles, there's no indication that spacer or the can itself is also stainless steel. So there's no indication that hardware affected the performance of those cells with PF6 alone.
Okay, thank you. Next question. How can we ensure PE separator is fully wet? Are there any pre-treatments needed before the cell assembly step?
Yeah, so for our regular electrolyte, EC, DMC, 25570, the solvent system, we don't see any issue with wetting our polyethylene separators. So we use an 18 micron double-sided polyethylene separator system. And we don't see issues with wetting, which is just we add the electrolyte and we can see that it's being wet. We also have a step in that case that we stage the cells. So that means the stager undergoes different steps of applying a vacuum and then breaking that vacuum, which should break any bubbles that are within the stack or the jelly roll. So that aids in wetting. Before that, we also massage the cell if it's a stacked pouch cell to help with wetting. And then vacuum sealing helps that as well. And then of course the wetting step. So we don't see issues in general with our normal solvent systems. With some solvent systems, it may require different. We've seen issues with wetting with some maybe forget DEC or PC. I have to look back at what the exact solvent system is. But in that case, it was wetting of the polypropylene separator in coin cell. And we saw that when the drop was placed on it, it didn't even wet. There are some specialty separators out there that will wet with any solvent system. So that can be something that's done. But again, in general, with our normal solvent systems, we don't see any issues with wetting.
Okay. Is it possible to mention what is done to address the electrode curling?
Yeah, sure. So we have a jig, and I'm not showing it here. So one of the things that we've done is that we cut, we have like a manila folder. We have that kind of size of cardboard pieces. So we can place we die punch that folder with a anode die, and then we have a jig so that we can lay out the separator, then put one of the punched cardboard pieces down, and then we could slowly lay out the anode piece. So uncurl it and put it on top of the cardboard, then put another piece of cardboard on top, and then fold the separator over and do a similar thing with the cathode. So it might only need one cardboard piece, maybe on the other side in the case of the cathode that was punched, and then tape over the whole stack. Now, obviously, you don't want to test the cells with the cardboard in it, so then the cardboard can be just slowly removed. So from the stack, and so when the cardboard's gone, it lays sort of flat because the anode and the cathode are curled in opposing directions. And also the tape and having the assembly helps it to flatten as well. It's still not completely flat. But after that, we make sure just by visualizing the anode and the cathode that it has good alignment as well. And then the anode, the tab, and the cathode tab are welded. And then we check the alignment again before putting that single layer stack into the pouch.
Okay. What are the typical CE numbers in the first cycle for single layer pouch cells?
I don't have them on hand, but so I would say they're similar to the multi-layer pouch cells. I don't think there's anything showing that they were any different. So yeah, there could be. It could, in fact, be the way that so both bookends or anodes in our multi-layer pouches have anode on the backside. So that might even slightly decrease the FCE as compared to a single layer pouch. So they could be even higher. I'd have to check the data on hand, but there is nothing. What I recall, there's nothing surprising from the data that said that the FCE was too low. So it was just normal FCE, whatever it wouldn't have been in that case, like 90% or something.
Okay. Do you use winding pins when you wind your cylindrical jelly rolls?
I'd have to check with our team on that. I don't exactly know those specifics.
Okay, we're going to have somebody respond in the chat on that one.
Okay.
Thanks, Andrew. On slide 27, how is the maximum volume of the electrolyte determined? Is it limited by the internal pressure of the cell upon aging?
Yeah, so usually we just go above a little above that minimum recommended fill volume. We don't want to increase it more than that. We don't generally have things go to such a high pressure that the safety devices, like the vent, starts opening, or so that does not seem to be an issue. We have filled things that almost overflow in an 18650 or 2170, and it seems to be fine and not building up too much pressure. But that being said, we just want to go just a bit above that recommended fill volume. You will reach a point, as I mentioned, that indicates that there's too much fill if it just starts overflowing, and there's some cells, and we've done tear downs of some commercial cells that we've seen a lot of electrolyte in there. So just to fill it, but not overflow it.
Okay. Someone asks, we are trying to scale from coin cells to single layer pouch cells in our lab. Could you please explain a bit more about how we could combat or control the electrode curling after calendering, which you already spoke to a bit. Secondly, within the lab constraints, there is a way for us to weld the tabs in a good and reproducible manner.
So yeah, so the electrode curling is you cannot stop that. So I do not recommend using non-calendared electrodes because then you'll run with issues of just that resistance in the electrode. There might be some more polarization within the charge discharge curves. You probably see the delta V going higher if you decrease if you don't calendar. So I wouldn't do that for the single layer pouches. So it will curl. It just, as I mentioned, if you just find a way to carefully make those cells would be the best way. And for us, it was having those cardboard pieces in between. And for the welding, I showed the ultrasonic welding. I think that's probably the best way of getting that weld, because that way you'll achieve a weld that's the same as the multi-layer pouch. If you don't have access to a welder or limited access, there's another way of building these single layer pouches, and that's using a secondary current collector. So using a thicker, it's almost like a shim stock of aluminum and copper foil for a secondary current collector. The electrode can be placed on that secondary current collector. It possibly could be slightly taped on a separator piece, and that how to make those pouch cells is outlined in a paper by Matt Garrett, published by Jeff Dunn's group. So that would be another way of making those single layer pouches. In that case, you would use that current collector and weld the tab. So if you had some access to an ultrasonic welder, you could weld a bunch of different secondary current collectors. That could be an option as well. But that's a different design from ours.
Thanks, Andrew. Just a couple more questions. Do you have capability to do 3 electrode measurements?
Yep, we do. We have done 3 electrode measurements. We use copper wire in the electrode stack, and then that's slightly plated with lithium to provide the lithium reference electrode for those 3 electrode measurements. And if you want more data on that, you can reach out to us.
Great. Have you observed electrolyte loss in the coin cell? And do you add vacuum epoxy to reduce mass losses?
Yeah, so we don't. The electrolyte that we add initially ends up being, it's about 100 microliters in a single coin cell, and it ends up being a crazy amount of volume per amp hour. So it's a highly flooded coin cell. We have our crimper for our coin cell adjusted so that it provides a good seal. We don't see any electrolyte loss. Our normal coin cells, as I said previously, our normal coin cells are just used to determine FCE. If we are doing some more cycling and it's beyond a month, we still don't see electrolyte loss in general if we're running at 25 degrees or 40 degrees Celsius. Um, we've heard that you can run into issues if you're going even higher than that. So that would be FSI salt to enable even higher cycling. In that case, we've seen epoxy be used. We've tested differences with using epoxy around the seal to be added. And in our case, we didn't see any difference in electrolyte loss, but that would depend on your case as well, because the crimp could be slightly different or the hardware could be slightly different. So I just evaluated anyway. So yeah, we just made some cells. I don't know if they might have been just dummy cells with nothing in it, but just evaluated the amount of electrolyte loss by weighing, and we didn't see any issues with our system.
Okay, and last question. Do you always recommend the coin pouch can pathway for development, or do different battery materials require different strategies? For example, a new electrolyte additive versus a novel cathode binder material.
Yeah, so the um as I mentioned, like the coin cells usually we don't the the different cell types aren't necessarily a pathway to go from one to the next. So it'll depend specifically on your project. If it's a new cathode material and you only have a little bit of material, then maybe we could evaluate that in a coin cell or a single layer pouch cell. Um, but we always recommend the optimum way for us to evaluate your materials would be in a standard 1 amp hour pouch cell. We get the most consistency with those materials. And to do that, we just need some initial data from CoinCell, unless you could provide that initially already. And then in terms of cylindrical cells, that's usually a customer request to do cylindrical cells if they want to see the performance of how it performs in the cylindrical cell format.
Great. Thanks so much, Andrew. And thank you to everyone who joined us today and shared your questions during the Q&A. We hope you found the session informative and valuable. As a reminder, we'll send out a link to the recording tomorrow. If you'd like to dive deeper, we encourage you to watch our previous R&D webinars, where Andrew discussed NOVONIX's approach to electrode coating and how our R&D services can support your work in developing new battery technologies. You can find this on our website, and we'll share a link to this as well in the email. To stay up to date on future webinars, research, and services, you can also follow us on LinkedIn at NOVONIX. On behalf of the entire NOVONIX team today, thank you again for joining us. If you'd like to discuss how our R&D services can support your projects, please reach out through our site at novonixgroup.com. Have a wonderful day.